Alright, welcome to Unit 10. I know it says 9 here, but it is Unit 10, Chemical Equilibrium. Chemical equilibrium is a very important topic. It is very important that you master chemical equilibrium, Unit 10. We will be spending pretty much most of the rest of the year applying the concepts in Unit 10 to other situations. And so equilibrium, I would say, is going to be one of our biggest topics in the rest of the remaining of the year. To get us started in Lecture 1, we're going to talk about the basics of dynamic equilibrium and equilibrium state and what all that means. The essential questions that need to be addressed for this lecture is: what is a dynamic equilibrium? What is an equilibrium state? What is the equilibrium constant? Those need to be answered and addressed during this lecture, and you need to be able to apply those to a quiz that we'll have over this lecture. Alright, so before we begin, we're going to start out with saying a very important statement here, and that is that many chemical and physical processes occur in nature are reversible. Most of the time this year we have just looked at reactions going in a forward direction from reactant to product. But now what we're going to say is that reactions can be reversible. That not only do we form product, but the product itself can react and form reactant again. And we can kind of look at it like this. If I have a reaction, say with A plus B, and these are my reactant molecules, they can react to form the products of D plus C. However, D and C could collide with each other and cause the reaction to be reversed to recreate reactant again. Alright? So essentially what we could say here is reactants collide to form our product, and then the product collide through collision theory, go backwards to form our reactants. And with the terminology that we're going to look at here is that going from reactants to products is always known as the forward reaction. And going from product back to reactants is often known as the backward reaction. Sometimes the backward reaction is also known as the reverse reaction. So forward and backwards will reverse. This terminology we're going to use quite a bit throughout the remaining year. And so make sure you always understand that when we talk about the forward reaction, it is going from reactant to product, and the backwards or the reverse reaction is going from product to reactant. Okay? Now, this leads us into equilibrium now. Because processes, both chemical processes and physical processes, are reversible, this can lead us to an equilibrium state. And what do we mean by this equilibrium state? Well, essentially, an equilibrium state occurs, and I have an important point here, occurs when a reaction that is reversible, okay, reversible reaction, those forward and reverse reaction proceed at the same rate. All right? So as soon as the forward and backwards reaction are occurring at the same rate, we have hit an equilibrium state. And this can be seen by this graph here. It represents, we have up here our reactants, and NO2 is going to be our product. So the rate versus time here is what we're going to look at here. And you'll see that the reactant rate is going to slow down over time, and eventually it's going to level out. And then the product, it's going to increase, of course, because we're creating more product. It's going to go, the rate is technically going up, and then it's tapering off, and then it's going to become constant as well. Well, notice that at the point in which the forward, and this is the forward rate, becomes eventually equal to the reverse rate. When that happens, we've achieved what is known as equilibrium. And that constant rate is going to be carried on out over time. It's going to keep that up. And we'll never see a change in the rates as long as equilibrium has been established. All right. Later on, we're going to learn that equilibrium can be changed. It can be disrupted. And we can cause the forward or the reverse to begin to speed up and change. Okay, and we'll talk about that later. But for now, I just want you to understand that when an equilibrium has been established, both the forward and reverse reactions are occurring at the same rate. Now, two other points you can write down in your notes, fairly similar. As a system approaches equilibrium, both the forward and reverse reactions are occurring. And at equilibrium, the forward and reverse reactions are proceeding at the same rate, which we just kind of addressed. All right? So now we're going to go in and talk about this word dynamic equilibrium. Dynamic tells us that we have not stopped the reaction at equilibrium. The reaction is still occurring even though equilibrium has basically been established. Both the forward reaction is still going on and the reverse reaction is going on. The only thing is they're occurring at the same time, the same rate. All right? And so that's what dynamic equilibrium just means. Dynamic is the reaction has not stopped. All right? All right, so let's talk about what implications this all has for the concentration. From this graph, you can see the concentration versus time graph of our reactants and our products. All right, so let's trace this. Our reactant concentration is going to decrease over time until it becomes a constant. Eventually, it's not going to change anymore. And so the concentration of our reactant is going to stay constant and not change. Same thing with our product. Notice our product concentration is increasing, and all of a sudden it levels out and does not change. Now, this is because we've hit equilibrium. When equilibrium has been achieved, not only are the rates equal, but the concentration of both reactants and products are also going to remain constant. They're not going to change once equilibrium has been established. Very important idea right here. You need to make sure that you really understand, that when equilibrium has been established, the concentrations of both the reactants and products are going to remain constant, will not change. Okay? Now, this is referred to as the equilibrium mixture. Because those concentrations are constant, the equilibrium mixture gives us a lot of information, which we're going to learn about here coming up very soon in this lecture. All right, there are three things then that you need to understand at this point about chemical equilibrium. Number one is that when equilibrium has been established, the rate of the forward and reverse reaction are constant rates. They remain the same. However, it is a dynamic equilibrium. This is the second thing you need to know. Dynamic equilibrium, meaning the reaction is still occurring. And the third thing you have to really understand is that the reactant concentrations are constant. They remain the same once equilibrium has been achieved. All right? Now, this doesn't mean that the reactant and product concentrations are the same. All right, doesn't mean they're the same. It just means that once equilibrium has been achieved, they remain constant, just as they are, and will not change as they're at equilibrium. All right. All right, so now what we're going to do is look at a specific equilibrium system for physical systems. This would be like for physical changes, such as an example would be, say we're going to use water, H2O, and it's going to be in the liquid state. Now, we know that water, liquid water, can evaporate, and that is a physical process to convert it into a gas. This process of evaporation is noted in the forward direction. All right, but I think you're very well aware that this is a reversible process, because a gas can also go in the backwards direction to become a liquid again. It can be condensed, and so we call this condensation. All right. Now, there is a specific temperature point in which condensation and the evaporation that occurs will eventually hit at the same rate. And so when evaporation and condensation occur at the same rate, this is known as an equilibrium state for this physical system of evaporation and condensation. And so you can think of it as that the liquid water is going to evaporate at the same rate that the gas is going to condense back into a liquid state. All right, so it is going to appear to us that there's no change in the amount of liquid water versus the amount of gaseous water, because the concentrations will remain the same at equilibrium. We know that. But the process is still occurring, evaporation and condensation, because it's dynamic. And so we're going to see this still continue to go, okay? And so this is what a physical system would look like for an equilibrium state. Now, let's look at more of a chemical equilibrium state, and this is for chemical reactions. And you've kind of already looked at these graphs a little bit. And so here we got our reaction of N2O4, and in the forward direction it's going to create a product of NO2. All right? And balance that equation there. In the reverse direction, the NO2 molecules will collide with each other and create our reactant again of N2O4. Now, when the rates of the forward direction and the reverse direction are the same, then we've hit chemical equilibrium, as shown again by this graph. All right? And again, during a chemical equilibrium, during a chemical reaction, as we've stated already, so our a reactant going in this direction creates NO2. Our NO2 will then reverse the reaction, but when equilibrium has been established, the concentrations remain the same. And so, again, we're applying these three principles of dynamic equilibrium. The rates are the same, and the concentrations are constant at equilibrium once it's achieved. Alright, so now what we're going to do is get into what is known as the equilibrium constant expression. Absolutely important to know. We will spend quite a bit of time on solving problems that deal with the equilibrium constant expression. So first of all, let's talk about what the equilibrium constant is. All right? The equilibrium constant is, let's go back. Okay. The equilibrium constant, based on this statement here, and by the way, it's symbolized, the equilibrium constant is symbolized by a capital K with a small c. All right? So the equilibrium constant has a fixed value for a particular reaction at a specific temperature. And I'm going to highlight specific temperature because that's important. The Kc value, or the equilibrium constant value, is temperature dependent. All right? Which means the only thing that changes the value of Kc for a reaction is the temperature. All right? So every reversible reaction has a constant or an equilibrium constant Kc, and it changes from reaction to reaction. All right? Now the only thing that can change that constant is the temperature. So again, we call Kc temperature dependent. All right, so now what we're going to do is we're going to write the equilibrium constant, or the equilibrium expression here, okay? So if I had a reaction, again, say A plus B, and it's going to produce a reversible reaction with C plus D, okay? To write the equilibrium expression, to solve for the value of Kc, all right, to get that constant, what we are going to do is we're going to take the the products concentrations, C, and this is going to be, I'm going to put EQ to remind us that these are equilibrium concentrations, and D, concentration of D, EQ, okay, for equilibrium concentrations. And we're going to put it up to some power, C and D. All right? And really those C and D's are the coefficients to our balanced chemical equation over the concentrations of our reactants at equilibrium concentrations, EQ, to their coefficient power in the balanced equation. Here's the concentration of B at equilibrium concentration to B. Okay, so this is known as the equilibrium constant expression. And you need to become very familiar with this idea here. Okay, so let me use an example of all of this. Let's say, let's say we have a real reaction now. Let's say we have a reaction between H2 gas plus I2 gas, and it's going to form a reversible reaction with our product 2HI gas. Alright? So the equilibrium expression for this would be Kc for this reaction is equal to the concentration of our product, HI, and that would be the equilibrium concentration. And we're going to put it to the second power because the coefficient there is 2, all right, in our equation. And then we're going to put this over the reactants, so H2. And notice there's only a 1 coefficient for hydrogen, so it's going to be to the first power times the I2 concentration. And remember, these are all at equilibriums, EQ, equilibriums. And that's also to the first power because it has coefficient of 1. Right? So this is a real example of the equilibrium constant expression for this particular reaction to find the equilibrium constant, Kc. All right? So we can actually do a problem where we can actually just fill in the values, the equilibrium values, into this equation and find Kc. And we'll do some of those in class and practice this a little bit. For now, just make sure you know what the equilibrium expression is. Alright, so now we're going to dive into our very last topic, and that is dealing with the position of the equilibrium. Alright, now this is really an important topic to make sure that we end up with an understanding really well for the quiz that you're going to take on this, and understanding this in general for next lectures and previous topics that we'll look at with equilibrium. Alright, so I've written down some important points that you need to put into your notes on the equilibrium position. First of all, the equilibrium position refers to which side of the reaction at equilibrium has a higher concentration, reactants or products. Now remember, going back earlier in this lecture, we said that at equilibrium, the concentration of the products and the reactants are going to be constant. They won't change. However, that doesn't mean that the concentration of the reactants and products are going to be the same at equilibrium. That's not going to happen. All right? So usually when equilibrium is established, either the products have a higher concentration or the reactants have a higher concentration. And it's important to know which one is which, okay? And that's referred to as the equilibrium position. So, if the reaction mixture contains predominantly product, then the reaction is said to lie to the right. But if the reaction mixture contains predominant reactant, so most of the concentration is reactant, then the reaction is said to lie to the left. Alright? So again, if there's more products, more concentration of products at equilibrium, then the reaction, the equilibrium position lies to the right. If it is more reactant concentration than product, then the equilibrium lies to the left. Alright? And this is important because it associates with the K value. Okay? The equilibrium constant, or Kc. So, a large, let's erase that. A large K value, so one that is greater than 1, the reaction is product favored. Alright? So the greater the K value, greater than 1, the more product favor it is, and that means the product predominates at equilibrium, and the equilibrium lies to the right. Okay? That's kind of depicted by this, where we have more products than we have reactants, and so the equilibrium lies to the right. However, if the K value is smaller than 1, very small K value, then the reaction is reactant favored, and it means that the reactants predominates at equilibrium, and the equilibrium lies to the left. We have more reactants than products. The equilibrium is favored in the backwards direction. Alright? Here, they're favored in the forward direction. So here, the Kc value is greater than 1, and over here, the Kc value is less than 1, right, for this, right? So where the equilibrium position lies is an important aspect, and make sure that that this slide here, and in your notes, that you study this for the quiz and spend some time understanding the equilibrium position. Alright, so that is it for this particular lecture. We are done with lecture 1, and you are ready to go on to lecture 2 here. But again, I would go back and review these principles of basics on equilibrium and equilibrium state and so forth. Okay? So that is it for now.